So we know that electrons are found in these rings according to the Bohr model. And in the Bohr model, there's a great video about how these electrons move on YouTube. So do go and check out this video. It's hilarious and scientifically accurate. So let's draw a picture of a Bohr model to answer these questions. Okay, so recall that in a Bohr model of atom, we have a nucleus, and outside the nucleus we have electrons. And the electrons are traveling in these fixed paths. Now, the number of electrons in each ring cannot exceed a certain maximum, which is 2, 8, 18, and 32. However, sometimes they fill in a different order. And the lowest possible energy configuration is called the ground state, and that's exactly found on your reference table. So what happens when a bright line spectrum is produced is electrons begin in the ground state, but in comes some energy, and the energy excites the electrons. So then the electrons will go and they'll gain energy and jump to a higher energy level. So this electron may jump to the second principal energy level. That is called the excited state. But the excited state is fleeting, it's highly unstable. So then the electron will go and it will return back to where it originally started. But when it turns back to where it originally started, then then the energy that it absorbed originally will be released in the form of light. So we know that the characteristic of light is not seen until the electrons move from a higher energy level to a lower energy level. Now, the other choices are not good because the bright line spectrum is produced by electrons, so neutrons are not involved in this. The next question is very similar to the first one, but again we're asked for the characteristic color of light. So when we see light is emitted is the key point here. So again, we don't see the light until the electrons go from a high energy level to a low energy level. So the electrons, we see the light when electrons emit the energy, so they're not gaining energy. They did gain energy in order to lose it, but we're actually looking for just the light. So they emit energy when they are going to a lower energy level. Now the next question asks us to look and see which is a gain of energy. Now recall that when electrons absorb energy, they jump to a higher principal energy level. Now when we look at our choices, we have from 2 to 3. So that's from 2 to 3, that's a higher principal energy level. Then we have second to first, that's going down. We have third to second, that's going down. And we have third to first, which is going down. So the only energy transition that is increasing is choice 1. For question 17, we're shown a bright line spectrum. We're asked to identify the gases in the bright line spectrum. So to do this, it's simply like matching, very similar to identifying relationships in jet electrophoresis. So we want to match bands. So here in the unknown mixture, we have this line. This line matches with gas A. Since we found one match in gas A, let's look for all other matching wavelengths of light. So here we have this doublet here in gas A, and we see this in our mixture, and we have this line in gas A, and we see it in our mixture. So we see that gas A is one of the parts of our mixture. Then we have this line. Now when we look through our choices, we see that this line corresponds with gas D, as does this doublet. So we can see that gases A and D are part of our mixture. Now the next question asks us to explain the production of an emission spectra in terms of energy states and electrons. So that means that we have to include the word electron and either the word or a definition of an energy state. So I'll use the definition of energy states or specific energy states, the ground state and the excited state, to explain the production of a emission spectra. So here we know that electrons in the ground state absorb energy and move to a higher energy excited state. Unstable excited state electrons return to the ground state, releasing energy in the form of light. So again, when answering these types of questions, it's important that you pay attention to the in terms of part. So here we have electrons, and then the energy state is the ground state. And then, again, we also talk about the excited state and returning to the lower energy ground state and release the energy in the form of light. So just make sure that we hit all the points. And when it says in terms of, you either have to include the term or include a definition or a direct description of the term. Next question, we're asked to look at valence electrons of fluorine. So what we'll want to do is pull up fluorine from our reference table. So here on fluorine, we'll look at the electron configuration. Now the electron configuration is of the periodic table are always ground state. Now, the valence electrons are the outermost electrons in the highest energy, principal energy level. So in that case, the outside electrons are here. They're always to the right. So this is 7. For the next question, we have to do the same thing. Let's pull up aluminum. Here we have the ground state electron configuration of aluminum. The valence electrons, again, are the outermost principal energy level electrons. So aluminum has a valence of 3. The next question is simply the definition of an isotope. We know that isotopes have the same atomic number, but different masses. Now, recall that we can talk mass numbers are really protons plus neutrons, and atomic numbers are the same thing as protons. So in the next question, they ask us, again, a definition of isotopes. So they have a different number of the same element, but a different number of neutrons, so isotope. Now, the average atomic mass is defined as the weighted average of the naturally occurring isotopes. And that is essentially the same thing as the masses and ratios of the naturally occurring isotopes. The word ratio here is a fraction, and a fraction can also be a percent. For the next question, we're asked to show the correct numerical setup for calculating the average atomic mass of element X. And remember that the formula for calculating average atomic mass is essentially going to be the percent abundance times the mass plus the percent abundance times the mass of each isotope. So in this case, we start with 19.91% times a mass of 10.01. Now, sometimes they'll give us an exact mass, and sometimes they'll only give us an isotope mass. So the exact mass is 10.01. Sometimes they'll give us this value. Sometimes they'll only give us this 10 value. You use as much information as you're given. Since we're given an exact mass, we're going to use that in our calculation. And we're going to add this to the product of 80.09 times 11.01. Now, recall that these are percents, and percents are really out of 100. So after we do our calculation, we have to be sure to divide our answer by 100. You'll know you forgot to divide by 100 if your answer, the average, does not lie within the parameters of your smallest and largest number. So our average must lie between the value of 10.01 and 11.01. To get the answer, we simply have to go and put this in our calculators. Now, the answer we report has to be to the correct number of significant digits. Looking up in the problem, the masses are given with 4 significant digits, as are the percent abundance. So we need to record our answer to the correct number of significant digits of 4. So that would be 10.81. And our units are atomic mass units. We'll take the same approach for the correct numerical setup of the isotopes of carbon. When doing the correct numerical setup, it is a good idea to calculate your answer using your calculator. The reason why this is important is sometimes little details, in this case, dividing by 100 is often forgotten. If your answer doesn't make sense, in this case, fall between 12 and 13, then you'll know that you'll need to revise your equation. Finally, we're asked to describe, and this is very important, they even italicize it, in terms of subatomic particles found in the nucleus. So while subatomic particles found in the nucleus include protons and neutrons. And the difference between carbon-12 and carbon-13, so it has to include either protons or neutrons. Well, we know that both carbon atoms have the same atomic number or number of protons, 6. So they have a different number of neutrons.